Okay.
Yeah, welcome to our next talk here by Bedaka Goswami. Bedata is one of the, or is actually our first research group leader at the Cluster of Excellence. He is joining us today from India, where he is currently waiting to be able to get back to Germany to fully take up his position, but he's also working remotely. Bedata did his PhD and then also his postdoc in Potsdam at the Potsdam Institute for Climate Impact Research, and he's particularly interested in time series analysis, in complex networks analysis, in climate data, and I'm really looking forward now to your talk and get an update of what you've been up to.
Okay. Thank you, Philip, for a nice introduction. I'm also really happy to be presenting here. It's been an interesting conference so far, in my opinion, and lots of interesting stuff. And I hope that I'm also able to add a few interesting things to that mix. So I've titled my presentation as Inferring Climate Variability from Patterns Hidden in Modern and Paleo Time Series Data. I come from a background of what's called nonlinear time series analysis. And for those who are not familiar with, so in terms of climate, modern time series would mean anything that's from the time period of the last 50 years or so, and paleo time series would mean something that's telling us about climate, which is anywhere from a couple of 100 years ago to a few thousands of years ago to tens of thousands to millions of years ago. In terms of the structure of this presentation, I've sort of divided into two parts. Both parts deal with some element, some type of complex networks. The first part is what our group in Potsdam use the terminology of climate networks, and I'll briefly explain what's that about and give two examples, one from Nepal and another one which is a global example related to rainfall. In the second part of my talk, I'll talk about something called recurrence networks, which is a kind of a network that you can construct from a single time series. And in that, I'll present a couple of examples which deal with paleoclimatic records of climate. Okay, so if you now come to climate networks, what are climate networks? It's a kind of complex network that you estimate from observed data. So you can imagine that we have the Earth system here in the top left, and we can have measurements on this Earth system. This can be satellite data, or it can be weather station data. A lot of times we also use what's called reanalysis data, which was mentioned briefly in the talk yesterday on climate informatics. So reanalysis data is something that combines weather station data and satellite data into a new data product, which is uniformly distributed all over the globe. So you can see this grid, small black dots all over the globe. So those, you can think of them as measurement points. So every black dot in this top right corner on the surface of the Earth has a time series related to some climate observable, like temperature, rainfall, wind, and so on. So you basically have a lot of such time series which come from different parts of space. And what you can then do is you can take all possible pairs of these time series and do some kind of correlation analysis. Doesn't really have to be Pearson's cross correlation, but it can be more sophisticated methods like mutual information. You take your pick, but the essential idea is that you compare pairs of time series and you try to estimate whether they behave similarly or not. And if they are similar in their behavior, in their time behavior, then you put a link between those 2 points in space from where you got the time series. And if they are not, then you let it be. Essentially, then you get a complex network where the nodes of the network are the locations in space from where you got your time series from, and edges represent similarities in their time behavior. Okay. This is another example of how you can have such a climate network. So on the left panel, you see a map of Germany with the colored dots, so black and red dots represent weather stations in and around Germany, from where we had rainfall measurements, and using a similarity measure called event synchronization, the authors in this study, they constructed this climate network, a rainfall-based climate network that you see on the right, where you see these lightly gray shaded lines that connect bunches of nodes all over the place based on similarities in rainfall behavior. Right. So this is another example of how you can construct a climate network. So you're maybe what I want to say here is that your nodes do not need to be uniformly distributed in space and time. Right. So why use climate networks? It's I would say these are some of the main reasons that I feel they are useful for, is that they help us uncover non-trivial spatial patterns. And in climate, when you study climate, spatial patterns do play a very important role in the questions that we ask from climatic systems, right? Then they also reveal higher order features of the climate systems. So what I mean by this is that when you have the framework of complex networks in your mind, then you open up the possibility to characterize your climate system, not just in terms of means or variance or power spectra, but also in terms of network degree, clustering, edge anisotropy, communities, and so on, right? So it opens up a whole new way of looking at climate data. And this then follows to the third point, is that you can now use these list of new characteristics to see if climate models are reproducing observed climate variability properly or not, right? You can also use climate networks, come up with ideas how to use climate networks to group different climate systems as similar or non-similar. Okay, so this was a very brief overview on what climate networks are. I would now come ahead to the first example, where we work with some river discharge data from Nepal. So this is weather station data, so irregularly spaced, irregular distributed in space, and we have data from roughly from the late 70s to the late 90s, early 2000s, and it's in terms of the amount of data, it's a small data set. Here you can see on the top right and the map that it's roughly around 30 hydrological stations that have been measuring river discharge. And what we do is we, after some pre-processing where we ensure that the data follows a normal distribution, and then we decompose it and then extract some more interesting components of the data to study. We then do graph-based clustering on the data. So the graph here in this case is a climate network. So it's a network that has been constructed using Spearman's cross correlation between these 30 stations. And in the bottom right, you see what this weighted adjacency matrix, so to speak, looks like, where you have at least this bottom left corner is a very well-defined cluster that is not only a cluster in graph terms, in network terms, but it's actually also a cluster. It's coherently organized in actual observed space, right? So this basically corresponds to a particular river basin in West Nepal, Karnali basin of the Karnali River, which is also interesting because this the method itself did not really know whether these stations were closely gathered in space or not. It just tried to group together the weather stations based on similarities of their time series behavior. And what you find is that the Karnali Basin weather stations show coherent behavior, whereas the rest of Nepal doesn't. Now, why does this happen? And this is, again, I feel an important part of such data-driven approaches, that now that we have some insight into the climate system, we also have to now try and connect it back to domain knowledge. And so what we do in this particular case is we average the time series in the Karnali Basin to find some form of common behavior from these stations. And then this is what we get, which is, you can think of this as a river discharge index for this West Nepal region. And you can clearly see that there are several years where there were sort of very dry conditions, and there were several years where there were wet conditions in this region. We focus here on the dry periods, and we find that if you take the timings of these dry periods over this time span, and you wrap them on one year, you find that most of the dry periods occur in springtime, and so they occur with a much higher frequency in springtime, as you would expect from just randomly shuffling the same frequency of dry periods all over ideal year, right? And then again, now that we have found that that this region has these anomalous dry spring seasons once in a while, what climatic observers could underlie such pattern. We can, of course, look at different observables like temperature, which could influence snow melt in the region because it's near the Himalayas. We could look at precipitation, which could influence the river discharge. And of course, we could also look at wind patterns, which then also influence precipitation. In looking at these different variables, what we found is that wind patterns show a drastic change in these time periods of interest. So what you can do is you can look at wind fields at different levels of the atmosphere, and we looked at many different wind fields at many different levels of the atmosphere, and found that in upper level winds at 250 hectopascals, they show a drastic change in these time periods when you have dry periods in Nepal. And the change in winds actually results in a sort of a climatic border that runs right through Nepal. And here you can see this small irregular black shape is actually the Karnali Basin, from where we constructed the river discharge index in the first place. Right. So that's basically the main point of this example, is that I see that as being composed of three essential steps. First is, of course, pre-processing, where you extract relevant component from the data of what you want to study, and then climate networks play an important role in that. When you when you look at the data using the framework of networks, then you're open to ideas such as correlation-based clustering, and that basically allowed us to observe that Karnali differs from the rest of Nepal. And then the third step is where we go further. Now, once the statistical part is done, we go further and try to connect it back to domain knowledge, and we find that the anomalous dry spring times that are seen in Karnali are likely caused by the breakdown of upper level winds in the region. Okay, now I will come to the second example, which is related to extreme rainfall around the globe. Now, this is a completely different kind of a data set. This is a data set which is a high-resolution satellite-derived data set called TRIM, where you have daily rainfall data at 0.25 degrees all over the globe. Here, these two plots are just to give you a basic idea of how extreme rainfall looks like in this data set. So in the top panel, you see the 95th percentile of rainfall, which is also a standard definition for an extreme event in meteorological context. And in the bottom plot, you see the number of such 95th percentile events. And we are mainly concerned with the boreal summer season. So the northern hemispheric summer season, this is June, July, and August. Shaded areas in this region are are regions where in this period of June, July, and August, the shaded areas are regions where the number of extreme events were less than 3, so we excluded them from the analysis. Now, again, what we do is we take this data, which is, I think, in a total of around 570,000 time series, and we first convert them to event series, like series of binaries of zeros and ones, based on this definition of the 95th percentile of rainfall. And then we use a measure called event synchronization, which allows us to say whether the event, the spike train, the sort of extreme event spike train of one time series is similar to the extreme event spike train of another time series. And using that, we can then construct a similarity matrix, thresholding which we arrive at the adjacency matrix of the climate network that we want to study. After getting the network, what we find interesting for this study is to look at the link length distribution of this network. And this is what is shown here in this panel. You see the link length distribution of the extreme event rainfall network. What I mean by a link length distribution in this context is that here is, so what you see here is how, so if you are looking at a distance of say 1,000 kilometers, it means that it's much less likely to find a link of 1,000 kilometers that two observed time series around the globe separated by 1,000 kilometers. It's much less likely that their extreme rainfall are linked than, let's say, two time series which are separated by 100 kilometers. The important thing, though, to take away from this particular link length distribution is to see that it's clearly can be sort of has two different components. One is this power law decay in red, and a second component which is this bump that you see at very large lengths. These correspond to regional weather systems, which have typically lengths less than a couple of thousand kilometers, and the bump at the end corresponds to large-scale teleconnections, which is again a term common in climatological studies that denotes similarities in climatic behavior across large distances. It's also interesting to see that the teleconnection distribution here follows the same probability distribution as the great circle. So if this actually presents a problem in the sense that it makes it harder to test to test whether these links are statistically significant or not, because their distribution follows exactly the same distribution that you would get if you were to distribute links of such long distances all over the globe at random. So what we do is that we try to identify spatial patterns of these links, and that's what you see in this figure here, because what would typically be the case is that since climatic phenomena is spatially structured, certain regions of the globe would have a much higher likelihood of being connected to each other than others. So in this figure, what you see is that we take a small box in northern India and see where do links inside for nodes that are located inside this box in northern India. So where do the links from there go to all over the globe? And you see that they are sort of bundled up in these special regions, and each of this then has to be studied on an anecdotal basis, let's say, to understand the different climatic systems that could have led to each of these different bundle links. What we focus on is a link between southern Europe and northern India, and we find that extreme rainfall in these two regions are connected by something which is called the Silk Road pattern. And here you see again a demonstration of how the rainfall between these two regions are connected. So if you take all those days if you construct the rainfall anomalies of all those days where you see extreme rainfall in Europe, and say that all those days are day 0, and then you look at what's the situation 3 days later, then you see that now there's a blob of extreme rainfall occurring in northern India and Pakistan. Right? This is sort of a kind of a corroboration that what you see, the patterns that you see, the spatial patterns that are uncovered, so to speak, using climate networks, is not something that is abstract or an artifact, but then it actually can be related to observed climatological phenomena, and you can also actually connect it to ideas that already exist in climatological literature. Some of this example, again, climate networks help us to construct statistically significant links, form the network links, and the link-length distribution plays an important part in understanding how teleconnections are different from regional weather systems. And when we further try to look at the spatial patterns of links, we realize that these link bundles between Southern Europe and Northern India are connected by the Silk Road pattern, right? So in the second part of the talk, which is shorter than the first part, I will talk about something called recurrence networks, which is again a very different kind of networks that one can construct from time series. In that, you can take a single time series, and in this particular schematic, imagine that this blue line is the time trajectory of a system, a high-dimensional system in its state space. It's oscillating around some center, and then it goes again, drifts away somewhere else. And these black circles along this blue trajectory are measurement points where we measure the state of the system. Essentially, what a recurrence network does is it's basically a nearest neighbor network that sits in the state space of the system. So you can take each measurement point in your time trajectory and up to a small neighborhood definition of epsilon, you can look at where its neighbors are, and you can then link these three other time points as the neighbors of this red circle. And then you can go along and do the same for all observed points, and you end up with an adjacency matrix, which is basically a nearest neighbor network in state space. How can recurrence networks be used to study the dynamics of a system? One way of looking at it is to look at different systems. So here you have examples of recurrence, the adjacency matrix of recurrence networks constructed from different systems. So on the top left, you have white noise. Then in panel B, you have superposed harmonics. Bottom left is a chaotic system, and bottom right is geometric Brownian motion. So you see that these matrices really look, even visually, starkly different. And that is somehow the underlying principle of this recurrence network, which actually forms, which is part of a much larger framework called recurrence plot analysis, that these matrices can now be studied to understand the dynamics of the system that the time series comes from. I particularly focus on using recurrence networks to study abrupt transitions, and that's actually fairly intuitive to understand that if you have, let's say, if you consider a one-dimensional case where you have a time series where there's a sudden jump in between, and you now construct the distance matrix of all observed time points in this time series, you see that there's a clear two-block structure in this distance matrix, which corresponds to essentially two components of your graph, or in a more continuous sense, it corresponds to two communities in your graph. So identification of an abrupt transition in your data can be, now the question is, can be reframed as the identification of a two-block structure or a two-community structure in your recurrence network. We apply this concept to a special case where the time series themselves are in the form of a sequence of probability density functions in order to incorporate uncertainties, but that's a separate story. So in the top panel here, you have a time series of PDFs from which you can now construct not a binary, but a probabilistic recurrence matrix, which corresponds to a weighted network. And then you can slide a small window along the main diagonal, where at each location of the window you ask the question: is there a non-random two-community structure inside that window? And based on that statistical test, you can estimate a p-value, the dips in which will indicate a strong likelihood that you observe a non-random transition in that location of the window. And you see here, this is an artificial example where I imposed 3 transitions. One is a sudden jump, one is a slow decline, and the other is a complete change in the distribution itself. And these then are identified in these 3 dips in the p-value at the bottom panel. We apply this to paleoclimatic data from the Asian monsoon domain, which is basically southeastern China, and also the Kumph cave, which is in the Middle East, on the Arabian Sea. And you see the results here. So the dips in the p-value are essentially so-called abrupt events in these data sets. And the time period that we were looking at is the last 10,000 years, essentially what's called the Holocene, since it's the time that we have from the present up till the end of the last ice age. And in this analysis, what we were able to then again show is connected back to domain knowledge, that the events that we identify in our study correspond to events that were reported in the literature, essentially events that took place in Greenland. So that was an existing hypothesis that ice rafting events in Greenland affect the monsoon in Asia, and we presented a way of addressing this hypothesis on a statistically sound way. So to sum up this example, we used recurrence networks and communities in those networks to get transitions, and statistically significant dips in p-values were used to find time periods of non-random transitions. And once we had the identified transitions, we were able to again go back and look at in the literature and then address the hypothesis that the monsoon is affected by ice rafting in Greenland. We used the same approach to another data set, which is also from the monsoon domain, but not in the Asian monsoon domain, but more in the Indian monsoon domain, which is basically a cave, which is less than 200 kilometers from where I am right now in Meghalaya, the wettest place on Earth. And our colleagues got the data, and we constructed, again, a probabilistic recurrence network in this data set. And you see already this network has very interesting patterns, and you see a lot of block structures which would correspond to different transitions. So when we apply the approach, we essentially again get many events which are represented using these black plus signs on top, and the green squares and the red crosses correspond to, again, events in Greenland, which is always interesting to compare with the monsoon. And we find that even though the time period is different, this is in what's called the last glacial, where most of the world was covered in ice, between 30 and 44,000 years from now. Even in that period, these abrupt events in the Indian monsoon correspond to sudden warming in Greenland. And that is, again, why this is so is something that is we're still working on it and trying to understand and come up with reasonable mechanistic explanations of how this could happen. Which brings me more or less to the end of my talk. To summarize, I would say complex networks are rather useful in uncovering non-apparent structures in data. Climate networks in particular help to characterize spatial patterns hidden in multivariate data. Recurrence networks, on the other hand, help characterize individual time series that go beyond first and second moments. And at every point, I would say it's really very important when you are fundamentally a data-driven, using a data-driven approach is always important to be able to connect back to domain knowledge, because that's where you get the final confirmation of whether or not what you see is nonsense or not, right? And of course, there are challenges. How can we use climate networks and recurrence networks and such ideas with deep learning architectures? And something that I'm personally very interested in is how can we quantify the uncertainties of the final estimates in such really complicated analysis pipelines. Of course, all of what I presented here is collaboration with many brilliant people that I met in my time in Potsdam. Jürgen Kursner, Niklas Alyosha, and I did our PhDs together. Then Sebastian and Franziska, and Bodo, they're geoscientists who are really crazy enough to allow us to apply our methods to their data. And in the end, I would like to say that I'm now starting this new research group here in Tübingen, and with two PhD students, Felix and Jakob, who are going to start in September officially. And I also hope to be back in Tübingen by then, and let's hope that interesting things happen at this point. Yeah, thank you.
Thanks a lot, Vedanta, for your presentation and your insights into using data analysis and machine learning tools for climate science. We do have a couple of questions. The first one, let me find my mouse cursor. The first one is on your extreme rainfall patterns. So with the extreme rainfall patterns, is that something that would happen like during a thunderstorm? Or what is meant by that?
So technically, the definition of extreme rainfall would be something like this, that if at that particular location, we consider only those days which correspond to the 95th percentile or higher. So that threshold can be changed. It could also be 97 or 99. Whether or not they correspond to thunderstorms, I think there's no one answer to it. I think it can be due to one of many cases. So as you see here already in this link distribution, you get an idea that some of these things are really because of local regional weather systems, and some of these things are operating at a hemispheric level. So there can be different causes to extreme rainfall.
But is there some hypothesis why such an extreme rainfall event in Europe would be followed 3 days later by extreme rain in India?
Yes. So this is what I tried to. I went a bit fast there, but then the idea is that there are these jet streams at upper level winds, again at 250 hectopascals, which then are going all around the northern hemisphere, and the particular jet stream which connects Europe to India in this particular example is already known in the literature. It's called the Silk Road pattern, and more often than not, I would say, in my experience, when you are talking about connections that operate on such long spatial scales, it turns out to be some kind of a upper level jet stream.
Okay, thanks a lot. Some more questions here. So one technical question on the change point detection side: did you compare your recurrence method network? Did you compare that to more classical change point detection methods for time series? And what's the advantage?
In this particular study, we did not, but yes, in general, we did. So in some cases, let's say it would identify change points that is identified also by a classical change point detection. Let's say a Bayesian approach that tries to fit different trend lines and tries to find the optimal cut of the data where you can fit, or the optimal number of trend lines, let's say. So there, and if we were to apply our method to that data set as well, we would come up with the same answer. The focus in this case was that this can do more, as you also see in this example, that it also identifies a change point which corresponds to a change in the distribution of the data itself, which is which was our main message, that we were trying to come up with an approach which can also deal with uncertainties in the data. And in that sense, this is a bit novel, I would say, that it can be applied to data with uncertainties.
So the dog is in the house. Okay, so regarding the climate networks, here's another question by Alvaro. Are you mostly interested in identifying geographical clusters or a direction of influence in a multivariate time series? And if it's the latter, have you looked at something like partial directed coherence as a measure?
So I think that the direction of influence is something that would be the first step that allows us to construct the network in the first place. So if you were to use partial directed coherence, we would end up with a directed network that would also be very interesting to study. So there's no one single way of constructing a climate network. One can use different measures and they would sort of be able to showcase different aspects of the climatic system. With respect to the first question, we are, of course, interested in geographical clusters, but that's not the only thing. In fact, from our group, we have studies which are related to link length distributions. We have also more methodological studies where you try to also look at how the spatial embedding of the network influences your measures, right? So if you, for instance, that's actually quite interesting, and something that's not very apparent at first glance is that if you now look at Germany and you try to estimate the degree of this network on the right of each node, so nodes in the center, just by being virtue of their location in the center, they would show a higher degree because let's say if you compare a node here to a node there, they just have too few spatial neighbors to be able to connect. And so that's somehow an effect of the fact, it's an artifact, so to speak, of the fact that our network is embedded in a three-dimensional space. And so one can also study how that works. And we actually study many different things. We're interested in many different things.
Mm-hmm. Okay, and a final one. So when you detect specific structure in a network, do you try to assess how significant the structure is? So this relates to the first part of the talk. So these climate networks. Sorry.
Yeah. So we try to. Sometimes it can be a little bit complicated. So, for example, if you want to assess how significant this particular this particular partition of the graph is, I mean, if you have a very simplistic random model, it will turn out to be somehow naively statistically significant because the number of possible partitions is so high. But sometimes it really makes sense. For example, in this particular case, all of these spatial clusters that are connected to northern India and Pakistan are all of these bundles are essentially the result of a spatially resolved statistical null model, where we distribute. Let's say the block that we are interested in India had 1,000 links, so we distribute 1,000 links all over the globe and do that 10,000 times, and then see where do the actual observed links lie, and And then you see that, okay, the actual observed links do not just lie randomly, but they are actually quite significantly bundled up. So in some cases, it's possible to come up with a null model that allows us to assess the significance of such clusters, but in others, it's not so clear what to do.
Okay, thank you, Bedata.
Yeah, thank you.
And thanks for joining us from India. And then, yeah, all the best wishes from us to you and your family, and hopefully see you soon here in presence in Tübingen.
Yeah, I'm looking forward to. Thank you.
Now we will take another 15-minute break before we reconvene here at 5:30 with the final talk of the conference by Igor Lesanovsky from the physics department on neural network dynamics in quantum many-body systems. See you back then.